Good evening, everyone. Welcome to 125th video on misconceptions in physics. So finally, one of my deadlines, I thought maybe I would like to make only 100 videos. Now it is increasing day to day. Reaching to a target of 100 was quite difficult. But anyway, now we have reached 125. Thank you all for your appreciation, comments, and your replies to me. Okay, so my name is Ratankar Rao. I teach physics in a school, and my interest is to address the issues which one has while solving the numericals in physics. And the result is, as you see, so many problems. And usually, many students do write back to me and saying that, okay, these are the problems that they face. They're not able to understand, okay, or maybe resolve at the time of the examination. They commit a mistake. They don't know why do they commit a mistake and so on. The result is this. So usually what we see is there is one concept which is very similar, okay, to apply in two different contexts. And we need to identify what is the difference between the contexts. So that is what is the result of these videos. And hence, I looked at every concept which appears to be very similar from the question papers which the students make a mistake and thereby identify their potential mistake and then put it across as a video. Okay, so these are none of the problems are discovered by me or invented by me. So these are problems which has been documented elsewhere, maybe textbook, maybe past papers and so on. So I am just using those problems to illustrate what kind of doubts and where the students make a mistake. Okay, now without wasting your time, let me proceed further. Where is it? Yeah. Okay. So this problem is once again on logical reasoning errors. So long back we had started this. So this is your 125th problem video. And right. So using a kid of mass, okay, just a moment. Yeah. A kid of mass m stands at the edge of a platform of radius r. So you have a platform, a circular platform. Why circular? Because it has given us radius r. So circular platform of radius r, and then which can be freely rotated about its axis. So I'm going to put this axis assuming it's at the center, right? The moment of inertia of the platform is I. The moment of inertia of the platform is I, and the system is at rest. So which means initially it is at rest. It's not rotating. Okay, it cannot move, right? So therefore, the moment I say a system is at rest, so you should consider that the initial angular velocity is equal to 0. When the friend throws a ball of mass m, so what happens is there is a person who is standing here. He is standing, so he is standing here. Okay. Now there is one person who throws the ball from here. The ball reaches this person. What do you expect? Now, as a result of it, this rotating platform, which is free to rotate, is now rotates in this way. Rotates like this. Now it starts moving like this, right? It starts moving like this. Okay. If the velocity of the ball is v, the moment this ball is being thrown and he catches this. So why does it rotate? Because you are giving some energy. Now mark my terms. Okay, you're giving some energy. Who is giving? The ball is giving some energy. What is that energy? Half mv square. Half mv square. Kinetic energy. Now, because of this kinetic energy, what happens? The platform starts rotating. Okay, good. We have understood correctly. The velocity of the ball is v is horizontal along the tangential to the edge of the platform when it was caught by the kid. Find the angular speed of the platform after the event. The moment you catch it, then the platform starts rotating. Okay, so now what is he asking? What is the angular speed? What is the angular velocity? Simple. So what the student had done is he had applied a conservation of energy. Okay, now if we look at it in the first sense, it appears yes, you should have applied this one. Now the reason is because what is the energy given to me? I told you initially also, you are giving an energy of half mv square, which should now be equal to this energy before this ball hit the person or before the ball was caught by the kid, right? And this is the energy after the moment this energy was given. Someone has to do some work. Now who is doing the work? The kid is not doing the work. Kid receives the energy and the platform that was there, it started rotating. It is doing some work. Why do you say work? Because you're given some energy, it is doing some displacement, right? Okay. So this should now be equal to the rotational kinetic energy, which is nothing but half I omega square plus half m r square into omega square. Half m r square is nothing but this is again, once again, this is moment of inertia of the person. This is moment of inertia of the rotating platform, which is already given. So therefore, I get this, and this omega is the final angular velocity. Solving this, we get omega square equal to so much. Take omega is equal to square root of this one. This was the answer given. Superficially, when you look at the problem, everything appears to be right. Reasoning is correct. Everything is right. But this is incorrect. Now, why is it incorrect? This is a misconception. Now, let us look at it from another angle. Okay. Now, whenever you have a problem, look at it from two different angles. Very important. Okay. I do look at it. Okay. So, what if, what not, and so on. So, only then there will be a clarification piece. The problem they might ask you, they may not ask you, but to get a clarification, you need to look at it from a different angle. Now, what if this was not rotating? You take an object. Okay. You take an object. Let us say, this my cursor. Yeah. You take an object like this, a ball, for example, of mass m1, and you have another ball of mass m2. Mass m2. This ball was now started to move with a velocity, initial velocity u. It hit it, and after hitting, now similar to this scenario, after hitting, what happened? Both of these balls started to move. Okay, they stuck together. M1 plus m2. They are moving with a common velocity. Now, what is happening here? See, you threw the ball with a velocity u, and then when the moment it hit it, I wrote it as v here. The moment it hit the person caught the ball. Then what happened? The ball was sticking to his hands. And then both of them are rotating. Don't you think the analogy that I have described here and the analogy that you observe here, or the example that you observe here, both are identical, both are similar? The reason is because here there is a linear motion and here it is a circular motion. That's the only difference. Okay, but the examples are very much same. Now, do I apply my conservation of energy here? I never apply here. Why? The reason is because you call this as a collision and you say, this is my inelastic collision. Inelastic collision. Now, in this problem, if I ask you, what is the final velocity of the particle? Now, which principle do you use? Okay, you generally definitely use your conservation of momentum. You don't use conservation of energy. Why not conservation of energy? Because though I have given this object a velocity and energy to it, this energy strikes it, and as a result of it, this starts moving at a uniform velocity. Okay. Now, while these two join together, there is some internal forces here. These two binds together, right? They don't go separately. They bind together. When they are bound together, then some part of the energy is given to it. It is something like, okay, this is a spherical ball, this is another spherical ball. Okay. When it goes and binds it, look at my fingers. Now it goes and attach it to it like this. Right? It goes and attaches like this. And as a result of it, both of them start dragging like this. Now, what is happening is there is some energy being spent in attaching to the other object and going together over here. So, as a result of this, conservation of energy will not be used. Our energy is not conserved. The reason is because some energy is lost in attaching two objects. There is some cohesive force between them. Okay, and as a result of it, some energy is being lost. Now, this. So, in a similar way here, when the ball comes and hits into your palm, when you are catching it, now some amount of energy is now given to your palm over here because you are catching it. Now, that energy is not being sent to the wheel. That is the rotating wheel over here. So, as a result of it, you should not apply your conservation of energy. This is a misconception. Okay. Now, let us look at the actual solution. Now, what should I do? I hope you already got the solution. The solution is very simple. You just find out what is the momentum here, what is the momentum here. Now, which momentum? Now, something is rotating. When something is rotating, you cannot apply your conservation of momentum principle here. You have to apply conservation of angular momentum. Now, what is conservation of angular momentum? COAM. COAM is conservation of angular momentum. Which means what? Which means that the momentum before rotation, before collision, is equal to momentum after collision. Simple. Similar to that of this. Okay. Now, how do you find the conservation of angular momentum for a particle which is just moving like this linearly? There's no rotation. Simple way. If some object is moving like this, you start from here. Okay, I'm looking vertically like this. I'm looking vertically like this. When this is now making, so it is moving like this. Now, what do? We just turn our head like this, right? When we turn our head, then you find out what is the mass of the particle, velocity of the particle, and the radius or the distance of the particle. Thus, what you do is, you write the conservation of angular momentum is nothing but given by mv into r. mv into r. So, m is the mass of the particle, v is the velocity of the particle, and r is the radius at which it hit over here, when it is standing over here. mvr should now be equal to, what is the momentum of this, angular momentum of this one, which should be equal to I times omega plus what is the angular momentum of this one? This should be m into this is now rotating with some velocity, right? So how do I write this? So I write this as I into I dash into omega because both of them are moving the same velocity plus now what is I dash? Okay, let me write it off instead of this. Plus what is I dash here? That is the moment of inertia of the platform. Okay, let me write down separately. The momentum, angular momentum of the platform plus angular momentum of the kid who is standing on it. What's the angular momentum of the kid? Once again, this should be I kid multiplied by omega plus now the moment the kid has a ball in his hand. That mass is there, right? So this should be what is that? I mass into omega, which is nothing but ball for the ball. See, I'm not dividing anything here. Okay. So I'm just writing these values to make it clear. Okay. Now let us write down what are these values. Hey, I don't have space here. Okay. I'll write it down here. Where is my cursor? I'll write it down here. Now, I omega, I'll just retain like this because the value of I is already known, which is just I. I kid. What is I kid? Now, where is the kid standing here? Kid is standing here. Okay. And the distance from the center is R over here, which means it's equal to a point particle. Okay. So therefore, this should now be equal to mr square. Okay. For a point particle, you take a particle, put a string over here, then keep on rotate like this. Then what happens is the moment of inertia is this mr square. Then I mass. What is this I mass? The mass of the ball. Okay. The ball, which is in the kid's hand. Now the ball is also rotating along with the kid like this, right? And thus you can see this should now be equal to I mass should be mr square because it's also a point particle. Now let us substitute this. This should be equal to I omega plus mr square plus small mr square into omega. Now what do I need? I need the value of omega. So because angular velocity, which implies omega should now be equal to mvr divided by I plus m plus m plus m into r square. This is the expression for the final angular velocity. I hope you have understood this problem. Everything nothing obeys. Huh? Okay, fine. Yeah. So thank you, friends, for watching this. If you want to get a complete gist of all the videos, 125 videos, including today, to be seen together, then you can watch it from my website. My website ID URL, it's here. Okay, ratankar.com. And you can view this. So it's completely free. So don't forget to subscribe to my channel for all the updates. Thank you.